Hello, you're welcome to my channel once again. This is Chemistry with CK. I teach chemistry for O-level students, A-level students, GCSE students, as well as WASI students. Now, before we start today's lesson, we quickly want to do a recap of what we learned last time. Now, the last time we learned about what? Electron configuration. We learned about how to write the electron configuration considering all the four sets of quantum numbers. So now we were using this notation, the orbital notation, to write electron configuration. And what we have said or what we learned was that before you can write electron configuration, you must understand three rules, which we are saying we have the above principle. So the above principle states that in order for you to fill this, you must always fill the lower energy level before what? The higher energy level. So you must make sure that you fill the 2s before coming to fill what? The 3p. Again, you also must make sure that you fill the 4s before coming to fill what? The 3d. Then we also looked at Pauli's principle, which we said that Pauli's principle states that no two electrons in an orbital must have the same set of four quantum numbers. What this law means is that the total number of electrons that must fill an orbital must be 2 and must have what? Opposite spins. Now, the third that we saw was Ohm's rule of maximum multiplicity, which is saying that we have certain orbitals which we call them what? Degenerate orbitals. And these degenerate orbitals, for instance, when you come to the 2p, when you come to the 2p here, the 2p comprises of 2px, 2py, and what? 2pz. The 3p also comprises of the 3px, the 3py, and the 3pz. So these are called degenerate orbitals. The 3d also comprises of 3d1, 3d2, 3d3, 3d4, and 3d5. So we call these the degenerate orbitals. Now, according to Hooke, when we are filling these orbitals, you don't fill them 2, 2. No, you fill them 1, 1, 1. So degenerate orbitals must be first filled singly with electrons before you pair them up with what? Opposite spins. So that was what we learned. And as well, we also learned about how to write electron configuration. Today, our focus is going to be writing electron configuration, considering what we call, or we are going to consider the transition elements. So, we want to look at how to write the electron configuration of the what? First series of transition elements. And when we talk about this, we talk about from scandium to zinc. So, the last time we looked at for the first 5, but some of you told me to go back, so I'm going back. So now, before we start or before we write the electron configuration of the transition element, which we are saying scandium, let's quickly look at how we write the electron configuration for calcium. Now remember, calcium is not a transition element. Take note, it's not a transition metal. So in this calcium here, It tells us that the electrons here is what? 20. We are having 20 electrons present. So how will you write the electron configuration? So here, you're going to write 1s2 is full, then you move to what? 2s2. Then you move to what? The p orbital. We are saying that you then move to the 2p. But under the 2p, we have what? The 2px, the 2py, the 2pz. So we have 2px, p2py, p2pz. So this one will take 2, 2, 2. Then now we move to what? The 3s orbital. So 3s will take 2. After that we move to the 3p orbital. So also with the 3p, we have the 3px, 3py, and 3pz. So this one will take 2, 2, 2. Then after the 3p, we move on to the 4s, which is going to take 2. Now we are saying that we can also condense the transition or electron configuration. How do we do that? So this will be 1s2, 2s2. Now the 2px, the 2py, and the 2pz, we are now going to call it what? 2p. So here is going to be 2p6. So when we use the word p, it means we've combined the x, y, and what? Z. We've combined the direction, the orientation. So this one too can be 3x squared, so 3p what? 6. But whoa, the moment you bring x here, you are wrong. Why? Because when you bring x here, it means you are only specific to the x orientation. But without the x, we assume that we've combined the x, y, and z. And this will be 4s2. So this is the electron configuration of what? Of calcium. Now, we want to look at scandium, which is 21. So how would the electron configuration of scandium look like? So we will follow suit. 1s2, 2s2. Now 2p, since we have the px, the py, and the pz, we are going to have what? 2p6. Then we come here, 3x squared. After that we move to what? 3p6. And now you understand why the p are taking 6. Because we are saying you have the px, the py, and the pz. So then you move to what? The 4s orbital, which will take 2. So now let's count. 2, 4, 10, 12, 18, 20. Left with the 3d, which will take 1. Now, don't forget that the 3d, we are saying that we are having what? 5 orbitals. So this 3d here, when we expand the 3d, we have the 3d1, 3d2, 3d3, 3d4, and 3d5. So here, the 3d1 is the one taking the 1 electron. So when the 3d1 takes the 1 electron, this part, they are going to be 0, 0, 0, 0. Why? Because it is left with 1 electron. But however, when I say 3d, it means I've combined these 1, 2, 3, 4, 5, these 5 orbitals. Take note. So this should have been the electron configuration of what? Of scandium. I'm using should because we fill the void before what? The 3D. Now, however, by agreement, by convention, by standard, now after you writing the electron configuration, we want you to group the principal quantum numbers 1s, 2s, and the 3s. So this is how our final answer should be. So we have to write the electron configuration of scandium to be 1s2, 2s2, 2p6, 3s2, 3p6. Now, this 3d1, you have to come and group it to the 3s. So the 3d1, 4s2. Now we do this by what? By convention or by convention, by agreement. But you are to know that what? That the 4s orbital is filled before what? The 3d orbital. But after filling it, you must arrange the 3s, the 1s, the 2s for us. Take note. So most of the time, I tell my students, so now let's look at titanium, which is 22. So what we are saying? So this is what we are going to do is 22. So 1s2, 2s2, 2p6. Then we come to what? 3s2, 3p6. So this is what I mostly tell my students to do. Write the 3D, but don't fill it. Then go and fill the 4s2. So when you go and fill the 4s2, whatever is left, you come back and you fill the 3D. Which we are saying, this will be saying 3D what? 2. Now, due to space factor, I would want us to expand only the D for us to see something. So quickly, let's go back. So now, here, okay, vanadium, which is 23, will be written as what? 1s2, 2s2, 2p6, 3s2, 3p6. Then what is left? Write the 3D, don't fill it. Go and fill the 4s2. Then now, come and fill the D, which is what? 3D3. So what we are trying to say is that when we say 3D, so when I expand, when I say 3D1, this means that the 3D here, remember I told you that we have what? The 3D1, 3D2, 3D3, 3D4, 3D5. So these are the orbitals of 3D. There are 5 orbitals. So the 3D1 here means this one here will have 1. The rest here will be 0, 0, 0. So what we are saying. So here 3D2. So 3D2 here, when you expand it means we have 3D1, 3D2, 3D3, 3D4, and 3D5. So here, these 2 electrons, according to Holmes is saying that you have to share it singly, 1, before you come up and pair them. So 3D3 will go this way. So now, the next one will be what? Chromium. Now, quickly, let's look at chromium. So chromium here has atomic number 24. So this will be 1s2, 2s2, 2p6, 3s2, 3p6. What did you do, or what do you do? Write the 3D, don't fill it. Go and fill your 4s2, and now come and fill the D. So the chromium, we are supposed to have 3D4 and 4s2, which in this case is wrong. This tells us that there is an exception when you come to chromium. What is the exception? Now, for us to understand the exception, we have to expand the 3D for you to know what we are talking about. So for us to understand this exception, I want to take these 2 orbitals here. Remember I said that the 3D is made up of 3D1, 3D2, 3D3, 3D4, and 3D5. So this means how many electrons are here? The electrons here, it means this one is having 1, this one is having 1, this one is having 1, this one is having 1. But this orbital here is having 0. Let me use the box for you to explain. So this means this one is having 1 electron, 1 electron, 1 electron, 1 electron. It means all the orbitals are having 1 electron with the exception of what? The 3d5. And that causes what? Confusion. Because as human, if you give birth to 5 children and you are able to buy 4 items for 4, what will the last child do? So what happens is that for chromium always go here. It will go to the 4s orbital, take 1 electron. So when it takes 1 electron, chromium becomes what? 3d5. So now this one will have it, and the 4s now becomes what? 4s1. So we call this half field stability. Now, as you can see, all of the orbital, the 3D orbital are having one electron. And now chromium is stable. So when it comes to chromium, since chromium will have half of stability, the 3D orbital will be 4 instead of 3, it will be 5, sorry, instead of 4. Why? Because chromium wants to be half filled, and it makes chromium stable. Take note. So quickly, let's look at manganese. So manganese here, 25, 1s2, 2s2, 2p 6, 3s2, 3p6. Write the 3d, don't fill it. Go and fill your 4s2. Now left it 5. Now it's 3d 5. Then from chromium, from manganese, we come to iron. This is 26. 1s2, 2s2, 2p 6. This is 3s2, 3p6. Write your 3d, don't fill it. Your 4s2, now 3d6. From what? From your iron, then go to cobalt. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, don't fill it. Go to 4s2, 3d7. Now from cobalt we go to nickel, which is 28. So now with nickel you have 1s2, 2s2, 2p6, 3s2, 3p6. Write your 3d, don't fill it. Go and fill the 4s2. Whatever is left, come and fill the 3d8. Then we go to copper. Now when it comes to copper, the same exception that was in chromium, we do that to copper. Why? Now let's go here. This 1s2, 2s2, 2p 6. And this 3s2, 3p6, 3d don't fill, 4s2, 3d9. So when it comes to copper, you can see that the 3d orbital of copper is 9. Now, let me expand it for you to understand. So when we say 3d9, what does this mean? This means that we have 5 3d orbitals. Remember, say 3d1, 3d2, 3d3, 3d4, and 3d5. These are 5. So according to who's is saying that for you to fill this 1, 1, 1, 1, 1. Then you have to come back and pair them. So this one will take 2, this one will take 2, this one will take 2, and this one will take 2. So when we talk about 3d9, 1, 1, 1, 1, 1, and this one 2, 2, 2, 2. So you can see that when it comes to copper, the 3d5 orbital here has only one electron, while the rest has 2. And this creates some form of instability. So what copper does it will go to the forest, take an electron. So when it takes an electron, this one now becomes 2, which is now, the orbital now becomes fully filled. Then the 4s1. That means the 4s will only have one electron. So the exception which was in chromium goes or comes here as well in copper, due to what we called fully filled d orbital. Fully filled 3d orbital. So take note, when it goes to chromium and copper, there is an exception due to what we call half filled in chromium and fully filled in copper. Take note. So now, this will be the electron configuration of copper 3d10 4s1. And the last but not the least is zinc, which is 30. So 1s2, 2s2, 2p, 6, 3s2, 3p what? 6. After 3p, write your 3d. Don't fill it. Go and fill your 4s2, then 3d10. So what we are saying is that we always fill the 4s before the 3d. But by conversion, by standard, by agreement, scientists have realized that after filling it, you have to group them for us. So you can see these are the ones, these are the twos, these are the threes. Now remember that I told you that the 1s orbital is found in what? The K shell. The 2s and the 2p are found in the L shell. The 3s, 3p and 3d are found in what? The M shell. So we are saying that the K shell can only take a maximum of what? 2 electrons. The L shell takes 8. Why? Because the S is going to take 2, the P will take 6, which will be 8. The M shell will take 2, 6, and 10. That will be saying 18. So when we were learning about quantum numbers, I told you the M shell takes 18 electrons. But when you were in JHS junior high, you were told that the M shell takes 8. No. The reason is that from hydrogen to calcium, which is 20, you don't have the 3d orbital. The 3d orbital comes in from 21 to 30. So the reason why we are saying it is stable with 8 is that the 3d orbital is not found in the first 20 elements. Take note. So the M shell will take what? 18 electrons. And this is what we call electron configuration of the first series of what? Transition metals. Okay. Now, we also have another way of writing the electron configuration using a box and a spin. So in chemistry, we use box and spins to write electron configuration. And the spin is an arrow like this with one-sided arrow. So what we are saying is that this represents an electron. So quickly we write hydrogen as 1s1. But when you are using the spins or in the box, you write the 1s, then we draw a box, then you put one arrow facing up. Now, what we are saying is that these things, they face up and they face up. There must be only 2 inside the box. They cannot exceed 2. So now let's go to helium. Helium we are saying is 1s2. With the box and spin, helium will be written as He. That is what? 1s. So in our box, how many spins are we going to have? We're going to have 2. One spin facing up, one spin facing down. Now, with lithium, which is 1s2, 2s1, with our spin, we're going to write lithium as what? 1s, one spin facing up, one spin facing down, 2s, one spin facing up. So each spin represents what? An electron. So each spin will represent an electron. So quickly, let's go. Beryllium, 1s2, 2s2. This is what we write. But using the spin notation, we are going to have beryllium, 1s, you draw your box, one spin facing up, one spin facing down. And go to 2s, one spin facing up, one spin facing down. Okay, so now we move on to what? Boron. So when we get to boron, boron is 5. So we would have written boron as 1s2, 2s2, 2p1. Now when it comes to the spin, we can also say 2p, but now let's look at it. When it comes to the spin, boron will be written as 1s, 2s. Now the 2p, remember with boron, the 2p you have what? 2px, 2py, and 2pz. These people, we said that they are degenerate. They are having the same energy. They are having the same principal quantum number. But what changes what? Their orientation. So with these people here, you draw a larger rectangle, then you separate them. So here, the one is for the what? The 2px. That means the 2py and the 2pz is 0. Take note. Now, let's go to what? Carbon. So carbon, 1s, the box is going to take 2. You go to 2s2, this box take 2. Then you go to what? 2px, 2py, 2pz. So here, according to Holmes says when you come here, you fill them, this will take 1, this will take 1, and that is for carbon. Nitrogen, you are going to have 1s, which is going to take 2, 2s, which also will take 2. Then you go to what? 2px, 2py, and 2pz. This will take 1, this will take 1, and this will take 1. That is what we write using the box and spin. So now 8 for oxygen, 1s, 2s, 2px, 2py, 2pz. When you come here, you give this one 1, you give this one 1, you give this one 1. Now a total of 7. Then now you come back and give this one 2. And that is what we use the spins for. So quickly, let's look at fluorine and neon. So fluorine, it is atomic number 9, 1s2, sorry, so 1s, we draw our box, that's 1s2, 2x, we draw our box, 2s2, 2px, 2py, and 2pz. Here, we will draw our box, so take 1, so take 1, which is what? 7. And come back, give this one 1, give this one 1, making this one alone, having it. Then we come to neon. So in this case, we are using the spin to represent what? An electron. And that's what we call the box and spin electron configuration. Take note. So now you should be able to use this to write any element, any of the transition metals. So quickly, how will we write that of what? Copper. Remember we said that copper is an exception. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, write it, but don't fill it. Then fill your 4s2, 4s1, sorry, 3d, there. So now, how will you write the box? The box is very, very simple. So your 1s, you give it, the electrons are 2. Your 2x, the electrons 2 are 2. Your 2p, remember we are saying that we have 3 of them. So 2, 2, 2. Then come to the 3s. You draw your box, you fill 2. Then come to your 3p. Divide it into 3 because there are 3 orbitals of the p subshell. This will take 2, 2, 2. Then when you come to the 3d, what did we see? We said the d, there are how many orbitals? There are 5. So with the d, we divide it into 5. 1, 2, 3, 4, 5. So your 4s, here will have 1 electron. Then when you come here, you fill the 5. So 1, 1, 1, 1, 1. And come and pair it up. 2, 2, 2, 2, 2. So this is the box and spin electron configuration for the transition metal copper. So you are just translating the idea here. But now in this place here, you are not going to use digits, but you are going to use boxes and spins to represent them. Now take note, the spins, they must always face opposite directions, like I told you. Whenever you see a spin facing the same direction, for example this, it implies that you have violated a law. And in this case, which law have you violated? You violated what? The Pauli's exclusion principle, because the Pauli's exclusion principle is telling us that they must have what? Opposite spins. The spins must be what? Opposite. Take note. So that is another way of writing the electron configuration using the box and the spin. Now, we also have a new electron configuration where we use the noble gases. Now, there are certain group of elements which we call them noble gas. Now, let me take you back to JHS. So what we are saying is that when you take example the K shell, we said that the K cell can only accommodate what? 2 electrons. It is okay, it is full. And what element is this? It's helium. When you go, we also said that the K can take 2, the L can take what? 8. So elements that have their atomic orbital or their shell being stable, I don't want to use the word full, being stable, we call them what? Noble gases. So what we are saying here is that we can write electron configuration using these noble gases. And how do we do that? Let's quickly look at how we do it. So now, when we write the electron configuration for hydrogen, that is what? 1s1. So when we go to helium, the electron configuration of helium is what? 1s2. Helium is a noble gas. So now, when we go to lithium, the electron configuration of lithium will be what? 1s2, 2s1. However, we know that the 1s2 always is that of the electron configuration of what? Helium. So this means that, or what we can say is that, it means a bracket. The bracket here means you put helium in bracket. When you put helium in bracket, it means that you are factoring the electron configuration of helium, which is 1s. So this helium in bracket represents the 1s. Then we go to what? Beryllium, which is 1s2, 2s2. So what does it mean? It means this 1s is the 1s of helium, then 2s2. Then when we come to boron, we have 1s2, 2s2, 2p, 1. So 2p1 here means that the 1s here represents the electron configuration of helium. Then when we go to carbon, 1s2, 2s2, 2p, 2. So using the electron configuration, since 1s is for helium, wherever you see 1s, you remove it and represent it by helium. Then we go to what? Nitrogen. 1s2, 2s2p3. So here, this is for helium, so He and that. Then we go to oxygen, 1s2, 2s2p4. So that means that the electron configuration of helium plus 2s2p4. Then fluorine, electron configuration Y is 1s2, 2s2p5. So this means the electron configuration of helium plus 2s2 to p5. Now we come to neon, 1s2, 2s2 p6. Now when we come to neon, we will not change this. Why? Because neon also is a noble gas. So now that means that when you get to another noble gas, it is going to take the what? The presence of the other. So now when you go to sodium, sodium will be 1s2, 2s2, 2p6, 3x1. So this means that we are going to remove all this. Why are we removing it? We are going to remove it and substitute by what? The noble gas of what? Neon. So now we are going to have the electron configuration of neon times what? Plus the 3s1. So this one here represents this. So what we are saying is that when you want to write the electron configuration using the noble gas, you must know. So for instance, so what are the noble gas that we know? The noble gas that we are talking about here is helium, which is 1s2, then neon, which is 1s2, 2s2, 2p6, then argon, 1s2, 2s2, 2p6, 3s2, 3p6. So what is so now if we want to what? We want to write the electron configuration of potassium. Potassium here is what? 19. Let's write that of potassium here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s what? 1. So if we want to use the noble gas notation, which makes everything simple, we will claim here, because this side is represented by what? The argon. So you claim all this part here, then you write into bracket Ar4s1. So this is the electron configuration of what? Potassium. Quickly, let's look at the electron configuration of manganese, which is 25. So here, at first, manganese, which is 25, the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 4s2, 3d5. So what do you see? But now we want to use that of the noble gas. So which noble gas is closer to manganese? The noble gas closer to manganese is what? Argon. So so argon is represented by this. So we are going to remove this, then write the electron configuration of argon plus what? Plus the remainder, that is 3d5 4s2. And that is how we write electron configuration using the noble gas. Now, most of the time, students prefer this electron configuration. However, if you use it to write an example, if you use it to answer questions in exams, we might mark you down. Now, why are we saying that? Now, if you are told to write the electron configuration of magnesium, someone can decide to write it as this N3s2. So when you write it as this in exam, you will be penalized. Now, what must you do? You must go on to explain to us what is this. So you have to, when you write the electron configuration as this, you must tell us that the electron configuration of helium is this. Without this explanation, where this means this, you will be marked wrong. Take note. So if I tell you write the electron configuration of carbon and you write helium 2s2 2p6, you'll be marked wrong. But if you go further to tell me that the electron configuration of helium is 1s2, you would be marked correct. So take note when to use the electron configuration of the noble gases, and you must always explain, or you must always write the electron configuration of the noble gas. Hello viewers, this brings us to the end of electron configuration. Now, if you have any question, you can put it in the comment section and feel free to like and share. Don't forget to tell a tired soul that there is God. Thank you and see you next time. Bye bye.